Hey guys, I just wanted to fill in the gaps here for those of you guys that missed Friday's lecture due to travel or other things. So what we covered was more of this molecular geometry stuff, and in addition to that, we also looked into a property called polarity. So I'm going to try to walk you through that. As I'm going through this lecture here, it's a good idea to have this Vesper geometry summary handout kind of close by, because that kind of guides you through the whole process. That's on slide number 10, I believe, from the lecture slides on Moodle, but it was also given as a separate handout, so you can look at that as a reference. Okay, so what I'd like to do is just briefly recap what we had talked about with. Let's see if I can get this going here. What I'd like to do is briefly recap what we had talked about in terms of our geometries that we presented about a week ago. Or actually it was Wednesday. So we had linear geometries, we had trigonal planar, and we were looking at tetrahedral geometries. So before you do the geometry for any molecule, you need to first do the Lewis structure. Okay, so let's do the Lewis structure first. And I'm going to start with three of the molecules that were on, this is page number 4 of handout 7-1, and this is problem number 6. Okay, so let's write that down. So handout 7-1, we're doing, this is problem number 6. And what we're doing is 6A. Okay, so I might not go through all these, but I want to go through enough that gets you caught up to speed here. So first I'm going to start with the Lewis structures, and I want to look at 3 different molecules at first. So we'll do CH4, which we determined its Lewis structure to be this. We also looked at ammonia, and we saw that had a Lewis structure of this. And then we also looked at water, and this one had a Lewis structure that looks something like this. All right, so we've got our Lewis structures. The next step is to figure out what the geometry is going to be, okay? And now there's 2 types of geometry. There is something called an electron pair geometry, and the electron pair geometry is basically associated with the arrangement of regions of electron density around the central atom. Okay, and by regions of electron density, there I'm being general. So it could be a lone pair, right? So it could be a pair of dots. It could be a single bond. It could be a double bond, or it could be a triple bond. Okay, but whenever I see those, I'm going to include them as simply one region. Okay, so let me show you how to do that. So if I go into my Lewis structures here, and I look at CH4, the first one here, I want to count the regions around carbon. So I would look at, I've got 4 bonds, so I would say 1, 2, 3, 4. Okay, it's got 4 regions of electron density. Let's check out ammonia. 1, 2, 3, 4. Okay, so it also has 4. Water, 1, 2, 3, 4. Okay, so you count those electron pairs and those single bonds as a region. Okay, if you had a double bond, like for example, let me just do a quick example here. If we had something like carbon dioxide, in that case we saw we had 2 double bonds. So if I wanted to count the regions of electron density around that one, I would say that carbon has 1, 2 around it, okay? So you would count the double bonds as a single region. Okay. So now we're ready to do our electron pair geometries for each one of these, okay? And they all have the same number of electron regions around them, which is 4. And the best way to arrange these 4 regions is a tetrahedron. So I'm going to draw the tetrahedral shape around each of the central atoms. So there's 2 in the plane of the board. The dashed line is going back. The solid line is going out at you. I do that for all 3 here. Okay. And so all of these are going to have the same electron pair geometry. So all have so-called tetrahedral electron pair geometries. Okay, now what about molecular geometry? Let's check that out. Okay, so for that we need to consider the connectivity of the atoms, okay? So what is the arrangement of the atoms in 3D space, not just the electrons? So let's see here. With methane, we'll go ahead and add in those hydrogens as it's in the structure. And for methane, this has a molecular geometry which matches the electron pair geometry. So our molecular geometry here is going to be also tetrahedral. The bond angle for the tetrahedral case is going to be 109.5. All right, let's check out ammonia. So ammonia, I got 3 hydrogens, so I'm going to put those down here. And then I have a lone pair of electrons. I'll put that on top. Whoops. Now, it doesn't matter where you put those lone pairs, as long as you put them somewhere. This shape is a little bit different. It's called a trigonal pyramidal shape. Okay, so if you look at that nitrogen and those hydrogens, it looks kind of like a pyramid. So its molecular geometry would be trigonal pyramidal. So let's write that down. Trigonal pyramidal. And it's going to have, again, the bond angle is going to be 109.5. All right, now let's check out water. I've got 2 hydrogens. Again, it doesn't matter where you put them per se, but I'm going to put them in the plane of the board there. And then I'm going to put my 2 lone pairs. One's going back into space, and another one is actually coming out at you. Okay, so that's what the solid and dash weds refer to. So in this case, again, my electron pair geometry is tetrahedral because I've got 4 regions of density. But my molecular geometry in this case is going to be, actually in this case it's called bent. So molecular geometry is bent. The angle for this one, again, 109.5. Okay. All right, so now let's look at some more complex situations. Okay, so if we go ahead and in your handout, turn the page to number 5, and let's look at a couple of these complexes here. I'm going to go a little bit out of order. Okay, so let's look first at PCl 5, and we always need to start with the Lewis structure first. So we determined that the previous lecture. Phosphorus is one of those that can break the octet rule, so it has too many bonds. Okay. If I go in and I count my regions of electron density around the phosphorus, I have 1, 2, 3, 4, 5. 5 regions. Okay. So whenever you have 5 regions of electron density, we know that we're going to need to form something called a trigonal bipyramidal shape. Okay. And the way that we're going to draw that is we've got, hold on a sec, give myself some space here. We've got 2 positions going up and down, so that's the so-called axial position. And then I've got sort of a triangle or a peace sign that's going in the plane of the board, okay? So one's in plane, and then there's one going back into space, and then one coming out at you, okay? So that's the trigonal bipyramidal shape. And in this case, we don't have any lone pairs of electrons, so we're just going to go ahead and connect all of those chlorine atoms to that shape. And you could put in all those lone pairs on the chlorines, but it's actually not needed if you're just trying to represent the geometry. In this case, we actually have 2 different angles. We have the angle between the axial positions, so this is our axial position, and then this is the equatorial position. And that angle is 90 degrees. And then we also have an angle in the plane, which ends up being 120. Okay, so you want to specify those 2 angles when you're describing the geometry. Okay, in this case, we're going to say our electron pair geometry and our molecular geometry are the same, because we don't have any lone pairs. So they both are trigonal bipyramidal. You can think of 2 pyramids on top of each other, one going up and one going down. All right, so now let's see what happens when we have a lone pair, okay? So let's check out, this is the last one on the list, which is selenium tetrachloride. So SeCl4. And I don't think I got this one in class for the Lewis structure, but if you do the Lewis structure, it ends up being selenium And we've got 4 chlorines. All those lone pairs there.